Hello viewers, welcome to this lecture on the MOOCs course on mathematical portfolio theory. In the last lecture, we had talked about probability space, both discrete and continuous. We had defined the properties of a probability measure and we had talked about random variables and some of its properties. In today's class, we will look at the first two moments in case of random variables, namely the mean and variance, and then we will talk about covariances and correlation coefficients. These two moments are of great importance in case of portfolio theory, because the entire structure of the modern portfolio theory hinges on the mean, which will be then related to the expected return, and the standard deviation or variance, which will be related to the risk in market conditions. So, we start this lecture number 2 by first talking about expectation in discrete time. So, first we talk about expectation, and we will talk in the context of finite probability space. And we will first begin naturally with the definition. So, what expectation are you talking about? We are talking about the expectation of a random variable. So, let x be a random variable as already defined over a finite probability space omega p. Remember, the omega was the sample space and p was the probability measure. With omega, now since this is a finite probability space, so I take my omega to be comprised of some elementary events omega 1, omega 2 all the way to some omega n. Then the expectation, or sometimes we call it mean or even expected value of the random variable, that is the random variable x, is defined as E of x with a subscript p to indicate the probability measure, and this will be given by the summation of x of omega I, that is the value the random variable takes for omega I, into probability of omega I, and summing this over I equal to 1 to n. Now, if the random variable x, it takes a certain number of distinct values. So, suppose it takes the distinct values, and I will enumerate them as x1, x2 all the way to xm. In that case, we have the expectation E of x subscript p to be summation of xi into probability that x takes the value xi, and in this case I will run I is equal to 1 to m. Okay. So, let us now introduce a certain notation. So, we say that, so let us denote the set of all random variables on the sample space omega with the notation RV of omega. Now, this is followed by a theorem, and we will see why you introduce this notation RV of omega. So, the expectation function right. So, we will basically now talk about the expectation function E from RV omega to R is a linear functional. So, I will explain what I mean by linear functional. I will say that more explicitly, if we have any two random variables. So, for any two random variables which are customarily we choose them to be x and y, and for any real numbers which we will customarily choose as small a and small b, we have the following result, that E of a x plus b y, this is going to be a into E of x plus b into E of y. Okay, now let us look at a proof of this, a simple proof of this. So, accordingly we have to start off with the random variable x and the values it takes. So, let us suppose that the random variable x takes the values say x1, x2 all the way to say x m subscript 1, and the random variable y similarly it takes the values say y1, y2 all the way to y m 2. Then the random variable, so we are interested in the random variable a x plus b y. What does it look like? So, the random variable, remember that any linear combination of random variables is also a random variable. So, this random variable a x plus b y, this will take the values of what form? It is going to take the values of the form a x I plus b y j with I equal to 1, 2 all the way to m 1 and j is equal to obviously I will go all the way to m 2. So, I equal to j equal to 1, 2 all the way to m 2. Okay, so, what we are going to do now is we will next consider the events. So, now we will consider the events and the events are what? The events are that x equal to x I and y is equal to y j. We will consider this event and we will introduce a notation for it. So, we denote it by say E I j. So, basically all combinations of this x I and y j, all these such events will identify them by E of I j. See here as before, I will be equal to 1, 2 all the way to m 1 and j is going to be equal to 1, 2 all the way to m 2. Now, these events as you can see, so the corresponding these events form a partition of omega. So, this is very crucial with the property. So, consequent to this being a partition of omega, it satisfies the property that a x plus b y has a constant value AXI plus BYJ on EIJ. So accordingly, so what we need to prove is basically we will need to prove this result, that E of Ax plus By equal to Aex plus By. So accordingly, E of x, we start with the left hand side. So E of Ax plus By, this is going to be, by definition, this is going to be, what is the random variable here? So this is going to be Axi plus Byj, this is the values it takes, along with the corresponding probability, that probability x equal to xi and y is equal to yj. So just remember that this x being equal to xi and y being equal to yj for I equal to 1 to m1 and j is equal to 1 to m2, these are actually disjoint and they basically form a partition. So I have just made use of the definition of what is the expectation in terms of the values that the random variable take in order to get this expression. So the summation now, this will go from I is equal to 1 to m1 and j is equal to 1 to m2. Okay, so now I am going to split this up into its components. So let me look at the first one involving the constant a. So this is going to be a into summation xi, I is equal to 1 to m1, and within bracket I will have summation j is equal to 1 to m2 probability of x equal to xi and y is equal to yj. Okay, so basically I have this term Axi which have been accommodated here along with the probability. Plus the second term, that is going to be plus b into summation j is equal to 1 to m2, this time this is going to be yj, and within the summation form I equal to 1 to m1, I again have probability that x equal to xi and y is equal to yj. So here I am basically considering the xi terms, and here I am considering the yj terms. So the summation here goes from I is equal to 1 to m1 and j is equal to 1 to m2 here, and here it is the other way around, j is equal to 1 to m2 and I is equal to 1 to m1. So now interestingly observe that since j, it runs from j equal to 1 to m1, so basically this probability will add up to 1, and here it runs from I equal to 1 to m1, so this is going to just add up to 1. So accordingly, what we have the next line is that I will have a. So from here I will have a into summation xi, I is equal to 1 to m into probability of x equal to xi. Note that here the summation only runs over j is equal to 1 to m2. So I am only left with probability of x equal to xi. In a similar manner, I will have the next term b summation j is equal to 1 to m2, this is m1, into yj, and here the summation runs from I equal to 1 to m1, so this adds up to 1, and so I am only left with probability of y is equal to yj, so this is probability of y is equal to yj. So now observe carefully this term here, this is nothing but by definition the expectation of x. So we obtained a of Ex, and this term by definition is the expectation of y. So I have b of expectation of y. So this completes the proof for the linearity of expectation. Alright, so next what we do is we will just make an observation. So note that, so let f from R to R be a real valued, so this is R. So this be a real valued function of a real variable. Remember, this is from R to R. And let x be a random variable. So, then I can now make the observation, then f of x which will be from omega to r, since x is from omega to r. So, f of x will be from omega to r is also a random variable. So, accordingly, once I have, so earlier I was talking about the random variable x or y, and I talked about the expectation of the random variable x and that of y. And now that I have defined what that if x is a random variable and f is from r to r, then f of x is also a random variable. So, the natural thing to do now is to define what is going to be the expectation of this newly defined random variable, namely f of x. So, this brings us to the next theorem, or you can treat it as a definition if you want. So, then the expected value of this newly noted random variable f of x is equal to, so this is going to be expectation of f of x subscript p as before. This is going to be, we take f of x omega I into p of omega I, and we run this summation from I is equal to 1 to n, and as before, if it takes the values x1 through xm, then this is simply going to be f of xi into probability that x equal to xi, and this time x equal to xi, and this time I will go from 1 to m. Remember that we had taken the random variable x to take the values from 1 through x1 through xm. Okay, so now what you want to do is that we have talked about the addition of random variables and function. So, this brings me to the next definition, which is the expectation of the product of random variables. So, let x and y be random variables, then the expected value of x y, this is defined to be, so for x y the random variable takes the value naturally x I y j with the probability that probability x equal to x I and y equal to y j, where I runs from 1 to m1 as before and j runs from 1 to m2. So, the immediate consequence of this definition is the theorem pertaining to independent x and y. So, if x and y are independent random variables on a probability space, omega p, then the expected value of x y is going to be expected value of x into expected value of y. So, once we have the definition of expectation in terms of a variable and as well as its linear combination, and we have talked about the expectation of the product of two random variables and what happens in case of both the random variables being independent of each other. So, naturally the next thing that we need to look at is the variance. So, accordingly we start the concept of variance and standard deviation. So, the first thing we will look at is we will look at the definition. So, again is the variance is for the random variable. So, let x be a random variable, and since we have already defined expectation, so we will put the condition that it is this has a finite expectation defined by say mu. Then the variance of the random variable x is defined as sigma x square is equal to variance of x is equal to expected value of x minus mu square. So, actually let us go back, let us define this by mu subscript x, so that there is no ambiguity. So, I will just define this as mu subscript x, just to identify that this is the finite mean of the random variable x. So, once we have the definition of variance, so further the standard deviation, so the immediate fallout of it is the definition of standard deviation. So, the standard deviation of the random variable x is defined as sigma x is equal to SD of x. So, SD is for standard deviation, and this is going to be square root of variance of x. Okay, so now that we have defined what is expectation and variance, so the next thing that we will do is that, and we have looked at a couple of properties of the expectation. So the next thing that we will look at is the certain properties of variance. So accordingly, we start off with this notion of properties of variance. So formally, let us say that let x be a random variable with finite expected value, then the following properties hold. So let me enumerate the properties one by one. So variance of x, and we will look at this definition of variance of x. This can be shown that this reduces, so the expression on the right hand side here, this reduces to e of x square minus mu x square, which is e of x square minus e of x whole square. The second property is that if x is a constant random variable, then the variance of this constant random variable var x, this is going to be equal to 0. The third property pertains to the scaling. So, for any real number a, variance of a x is simply going to be a square variance of x. The fourth property, this is about the additivity. So, if x and y are independent random variables, and this is very crucial, these are independent random variables, then the variance of x plus y, this is going to be variance of x plus variance of y. And finally, if c is a constant, then the variance of its scaling, that is variance of x plus c, is simply going to be the variance of x. So, I leave the proof as an exercise, just make use of the definition in order to prove them. Now, I just want to revisit something in the context of this fourth property and make an observation of how variance is distinguished from expectation in terms of one property. So, unlike expectation, variance is not linear, right. So, that means that if it was linear, it would have satisfied the property that variance of Ax plus By, this is going to be equal to A of variance of x plus B of variance of y, but this is not necessarily the case, as we will see later on for the expression of a linear combination of random variables. So, once you we present the expression for the variance of a linear combination of random variables which are not necessarily independent of each other, then you can easily see that this property actually does not hold. Okay, so I just now mentioned that we will look at the variance of a linear combination of the random variables, say x1 through xn. However, before we proceed on to do that, we have to talk about one more concept that will be required in order to have an expression for the variance of the linear combination of all these random variables, and that is basically the covariance. So, covariance is also, as we will see later on in the discussion of the modern portfolio theory, it is of great importance, where it will be related to essentially the joint behavior of the returns of the different assets, for example, stocks that will constitute a portfolio. But we will discuss the details of that as in when we start talking about modern portfolio theory. So, coming back to our current discussion, let us now move on to what is the definition of covariance. So, we will talk about covariance and one closely related concept to covariance, namely correlation. So, first let us start off with the definition. So, here if x and y are random variables with finite expectations denoted by, so we will denote them by mu x and the expectation of y to be mu y, and both of them are finite. So, we denote them by mu x and mu y respectively. Then the covariance of x and y is defined as, so the notation for this is a sigma x comma y, and it is also represented by COV for covariance x and y, and this is defined as the expectation of x minus mu x and y minus mu y. So, that is the expectation of the random variable x minus mu x and y minus mu y, where mu x and mu y are both finite expectations. So, let us quickly have a look at the properties of covariance. So, let x and y be random variables with finite expectations as before, and naturally this is as before, we will denote them by mu x and mu y. Then the following properties hold. So, first property is, it will be the definition of covariance of x and y and in terms of this value of the expectation, and we will give an alternative way of representing this. So, this will turn out to be equal to, so this expression that we have here, this will turn out to be E of x y minus E x into E y. The second property is that the covariance of x y is the same as covariance of y x. So, that is evident for the fact that covariance of x y is the covariance of this product of these two random variables, and covariance of y is again the product of these two random variables with the positioning of y minus mu y and x minus mu x being simply exchanged. The third property, if you observe carefully, if I take my x equal to y, then this will simply become E of x minus mu x square, which is the variance of x. So, simply covariance of x with itself, this is nothing but the variance of x. So, the fourth property is that if x is a constant random variable, then covariance of x y is going to be equal to 0. So, this is again evident from the basic definition of covariance, in which case in this case one of the expectations. So, suppose that here the x is a constant random variable. So, expected value of x, if x is the constant value c, then the expected value of x is also going to be equal to c. So, one of the factors in the definition of the covariance, that is x minus mu of x, that is going to be equal to 0, which will render the covariance to be equal to 0. Okay, so, the next come to the fifth property. So, for any real numbers a and b, covariance of a x plus b y, this random variable with the random variable say z, this is going to be a times covariance of x z plus b times covariance of y z. So, this will be used when you later on look at the portfolio theory and talk about the single index model. Finally, one property is that the absolute value of covariance of x y, this is going to be less than or equal to the standard deviation of x into standard deviation of y. Moreover, just one more observation. So, here this is the inequality. So, I need to sort of look at what happens or under what circumstance the equality will take place. So, moreover, the equality in this above relation, so the equality holds if and only if either one of x or y. So, one of the random variables is a constant, or if there are constants a and b for which y is equal to a x plus b. So, in the first case, if either of them are constant, then both the sides are going to be equal to 0 and the equality will hold, or the other circumstance in which the equality can hold is one of the random variables is a linear combination of the other in terms of this constants a and b. Okay, now, once we have talked about the properties of covariance, the next thing that we will look at is we will introduce the definition of correlation. So, again, if x and y are random variables with finite expectation and non-zero variances, and we will see once the definition is placed as to why we need non-zero variances, then the correlation coefficient of x and y is defined as rho x y is equal to covariance of x y divided by sigma x into sigma y. So, this is the because we have sigma x sigma y in the denominator, that is the reason why we needed to have non-zero variances. So, we note that using property 6. So, remember the property 6 was that the absolute value of covariance x y is less than or equal to sigma x into sigma y. So, if I bring this on the left hand side, from there it follows immediately in the context of rho x y, it follows immediately that absolute value of rho x y is less than or equal to 1, or this means that rho of x1 x y lies between -1 and +1. So, this is an important property. So, next we make one observation in the context of the fact that rho x1 lies between -1 and +1. So, rho x y, this assumes one of the boundary values of plus or minus 1 if and only if there exists a constant a not equal to 0 and b. So, there are actually two constants for which y is equal to a x plus. So, from this observation and the definition of rho that we have here, a couple of things immediately follows. Immediately it follows that rho x y, this is equal to plus 1. This implies that the slope of this line, that is a, is greater than 0, and for the other extreme value of rho x y, that is minus 1, it follows that the slope a is less than 0. So, let us now look at the interpretation of this. So, if rho x y is equal to plus 1, so this means that y is equal to a x plus b with a positive. So, then it means, so I am making this inference from the fact that y is equal to a x plus b with a being positive, in this case of rho x y equal to 1. So, then I can conclude that then y moves in the same direction as x. And likewise, if rho x y is equal to minus 1, so again I look at the linear relation and take into account the fact that the slope a is less than 0. So, then y moves in the opposite direction as x. So, one last interpretation remains, and this is again in terms of independence. So, if x and y are independent, then rho x y is equal to 0. So, it is obvious from the fact that if they are independent of each other, then covariance of x y, which is expected value of x. So, remember that we had this property of covariance of x y is equal to e x y minus e x into e y. So, if x and y are independent, then e x y is equal to e x into e y. So, covariance will become 0, and consequently naturally your rho also is going to be equal to 0. However, we need to be cautious that the converse is not necessarily true. Okay, now let me note down a couple of terminology that we will frequently use. So, the random variables. So, again this is related to the values of plus minus 1 and 0 of rho x y. So, the random variable x and y are uncorrelated if rho x y is equal to 0, perfectly positively correlated if rho x y equal to 1 and perfectly negatively correlated if rho x y is equal to minus 1. Okay, so we conclude this discussion on covariance and correlation with one theorem related to variance, linear combination of random variables. So, if x 1, x 2 all the way to x n are random variables on omega and a 1, a 2 all the way to a n are naturally the corresponding constants, then the linear combination, that is summation a I x I is equal to 1 to n. The formula for this is given by double summation I is equal to 1 to n, j is equal to 1 to n of a I into a j into covariance of x I x j. Okay, now let's so we have discussed elaborately on the discrete space. So let's now move on to continuous probability space and talk about the expectation and variance in the continuous probability space. As before, we start off with expectation and we have the definition first. So, let x be an absolutely continuous random variable having the density function. So, you have to specify the density function f of x. So, then the expectation or expected value or mean of the random variable x is defined as the improper integral. So, as before I will use mu x to give as the notation for expectation of x, and this is defined as the improper integral of minus infinity to plus infinity x into f of x dx. So, this is similar to summation x I into p of x equal to x I. However, we need the condition provided that integral minus infinity to infinity absolute value of x f of x dx, this is and finally, we come to variance. So, for this, so let us look at the definition. The variance of an absolutely a continuous random variable x is defined as was the case with the finite probability space. So, this is sigma x square is equal to var x, this is expected value of x minus mu x square, and consequently the standard deviation is defined as sigma x is equal to S d of x is equal to is defined as the square root of variance of x. Further, if x is a random variable and say g from R to R is a measurable function, then g of x is a random variable. So, recall that we had something similar in the finite space. Then g of x has the expectation given by, and the notation for this would be E of g x, and it is given by minus infinity to infinity integral f of x dx, of course for g of x dx, provided integral minus infinity to infinity of absolute value of g x into f x dx, this is finite. So, just to wind up this, we will just briefly note the properties both for expectation as well as variance. So, expected value of summation a I x I is equal to 1 to n. This is going to be summation a I e of x I. So, expectation satisfies the linearity property. Secondly, if x 1, x 2 all the way to x n are independent, then expected value of x 1, x 2 all the way to x n, this is going to be product of E x I is equal to 1 to n. The third property is variance of x is E of x square minus E of x whole square. The fourth property is that variance of summation a I x I is equal to 1 to n, this is summation a I square variance of x I is equal to 1 to n for independent x i's. And the last property is variance of x plus minus a is variance of x for some real constant a. So, this brings us to the end of this lecture. This lecture, just to recall, was focused on essentially three main concepts, namely the expectation, the variance and the covariance. For the expectation, we defined it both in the finite discrete space as well as a continuous space, and we did the same in case of variance, and we took the concept of variance and then we extended in case of covariance, and we defined what is the correlation coefficient, and all these concepts, that is the expectation, variance and the covariance as well as the correlation concept, they all basically form the fulcrum of the discussion of the modern portfolio theory. So, in the next class we will talk a little bit about estimation in the context of covariances, and we will talk about some important distributions that are relevant in the context of this particular course. Thank you for watching.